Okay, thank you for the introduction. Hi, everyone. So I'm Geoffroy Couteau, and this is a joint work with Elliot Boyle, Niv Gilboa, and Yuval Ishai. So with this talk, I'd like to start from the beginning. And when I say the beginning, I mean the very beginning. So perfect secure communication, Shannon 1944. If you want to send a message between two parties, how do you do? We know that you just have to share some long random keys between the two parties. So they just need the same key, and this key must be random and very long as the message. That's a cool result. In terms of key management, that's not perfect. You need to send your secret agent with this huge briefcase carrying this key around just to enable a one-time communication. Not so wonderful, but we also already know a solution, which is that using any pseudorandom generator, the parties only need to store some very short key, and then they can locally expand this key into a very long pseudorandom sequence. And so those pseudorandom sequences on both sides, they share some natural correlation, which is that they are equal. So very simple correlation. And that still suffices to enable secure communication, even though only computationally secure communication. So why did I recall all of that? Well, because I want to draw a connection with what I'm really interested about in this talk, which is secure computation. So in secure computation, now the task is a bit more complex. You don't want to just send a message. You want your parties, I will focus on the case of two parties, to securely evaluate a function on private inputs so that the transcript only leaks the output of the protocol. So natural question, can we kind of distribute keys to the parties? So random coins that would allow them to have perfect secure computation in the same way that we could have perfect secure communication with a one-time pad. And we know since 1995 and the work of Beaver that the answer is yes. By letting some trusted dealer generate and distribute correlated random coins before the protocol and give them to all of the parties can evaluate any function with perfect security. And those correlated keys only need to be essentially as large as the circuit you're willing to evaluate. And the correlation they need to satisfy now is not as simple as before. It's not just the same keys. It's a more complex correlation. For those of you who know about it, it's like OT correlation or Beaver triples. But still, that's a very cool result that was used in a huge number of work. Many of you in the room might recognize your name as one of the letters here. Yeah, not you. Doing MPC with first a preprocessing phase, which will generate those correlated random coins, followed by an online phase that uses those coins to get a very fast and information theoretically secure online phase. But now we still have this kind of unsatisfying key management issue, which is that the parties need to distributively generate and store a very large amount of correlated random coins that they will need to consume in the online phase. And that's still not entirely satisfying. So the dream here will be to have kind of the same thing as we have for secure communication, and to be able to let all our parties store only very small keys, say K0, K1, and then to let them expand those keys using some kind of pseudorandom generator into long random strings. But we would want now those random strings to satisfy some overall correlation, this say OT or Beaver triple correlation, or even more complex types of correlation. So can we do that? So before explaining what we know about that, I want to insist on the fact that if we could, that would be super cool. So most approach to efficient MPC now rely, as I said, on having a preprocessing phase during which we generate those long correlated random coins, followed by an online phase in which we consume those coins into an information theoretically secure and very fast secure computation protocol. Now, if you could generate instead very short keys and then locally expand them, so you will have three phases. In the first, you will have a tiny interactive protocol during which you generate and store small keys, short communication, short computation, almost no storage, very cool. Followed by only a local extraction procedure that would actually contain the bulk of the computation, where you would extend all those short keys into long pseudorandom but correlated strings. And then you could have the same very fast online phase. So if you can do that, The first consequence is that you strongly reduce the overall communication, because the bulk of the communication in standard preprocessing-based MPC is really in this preprocessing phase. Here, the preprocessing phase only has a tiny communication. Everything almost is local, just local work. And a second and even more important consequence of such an approach would be that it would make possible to have what we could think of as being on-demand MPC. So the idea would be as follows. Nowadays, if you want to if you think about doing MPC with someone, you can meet this person and start the preprocessing phase of some protocol. You don't know to need the inputs yet, but by doing this preprocessing phase, you're really committed to doing MPC with this person because you're investing a large communication, a large computation, and you need to store all those correlated random coins in the end. So somehow you really have to want to securely compute a function with this person to start a preprocessing protocol. That would not be the case anymore with this approach. You could meet many people around and just say, hey, couldn't we just do this tiny interactive protocol, generate short keys that cost us nothing, and that would enable a future secure computation protocol. This will have a very small storage, so you can think of it as just giving your business card. Like, okay, here my name is Jeffrey. We might want to do MPC later. Here is my tiny protocol. We exchange those short keys, and now, if later on we actually want to do some MPC, we can just retrieve those short keys, locally expand them in long correlated random coins, no interaction from here, only local work, and we can directly proceed with this fast, efficient online protocol. And a side benefit of all of that is that now even someone observing the network would not find out that you are actually willing to evaluate a function of this size with a given person. But with the current preprocessing approach, if you look at the network and two people are having this huge preprocessing protocol, you have a good idea of the size of the function they are planning to evaluate together. With this approach, this also entirely disappears, which is a desirable side benefit. So, okay, but what do we know about that? Well, the idea of compressing useful types of correlation that could be used in cryptographic applications and secure computation was put forth by Niv Gilboa and Yuval Ishai in 1999, where they showed how to compress linear correlations. So in the case of two parties, as I told you earlier, linear correlations, that's not so useful. It's just equality. But for multiple parties, it's more interesting already. So that's already something non-trivial, and it was followed by work by Kramer, Damgard, and Ishai in 2005 by a work that generalized that, and that showed essentially that you can locally generate a near arbitrary amount of pseudorandom Shamir secret shares of pseudorandom values. So this is quite useful in MPC, but what we would really like to have is a way to generate more complex types of correlation that we could use, for example, in two-party computation, like beaver triples. We know that we can do it from indistinguishability obfuscation for arbitrary types of correlation, but as you can already guess, that's not as efficient as you could dream of. For slightly more restricted kind of correlation that we can call additive correlation, which is essentially arbitrary function and then you share the output between the parties, we've shown 1 year ago with my co-author Elliot Boyle, Niv Gilboa, Yuval Ishai, and Michele Leroux, that's right here, that you can obtain these kind of correlations from a primitive known as homomorphic secret sharing. And this homomorphic secret sharing, we know how to build that under, say, LW or DDH. So standard assumptions. And also more recently, some work by Peter Schultz showed that you can also get close to having this kind of additive correlation starting from key homomorphic PRF, but you don't quite get to compressing additive correlation without any troubles. So, but about efficiency, typically focusing on our work, we had done a lot of effort toward optimizing that. So how efficient is that? We had done some back-end developed calculation back then because we wanted it to be our main contribution. It was a CCS paper. So we did some calculation, and if you have the help of a trusted third party, that gives you essentially almost everything you can need for the protocol. If you use an Amazon platform with 32 cores, then just compensating for the initial cost of the setup takes only a few decades. So we ended up pushing this very nice contribution to the appendix and didn't really mention it during CCS. It's still cool. So to sum up, if the goal is to get interesting types of useful correlation that we can use in the two-party setting, such as, say, Beaver triple or random OTs, we do not know of any real practical solution as of today. So the real dream will be to have a way to generate a large number of Oblivious linear evaluation, OLE. What's an OLE? It's a natural generalization of Oblivious transfer over a larger field. You have a field and over any field, in fact. And the sender inputs A and B to field elements, the receiver inputs X, and he gets AX plus B. And it enables, so having access to an OLE primitive enables secure computation of any arithmetic circuit the same way that OT enables secure computation of any Boolean circuit. And so the dream will be to generate many random OLE, where A, B, and X are all pseudorandom, starting from tiny keys. We do not quite achieve that, but that will be super, super great. What we get instead is a slight weakening of this. We focus on Vector OLE. So Vector OLE, that's a generalization of OLE where the input of the sender are two very large vectors over this field. And what the receiver gets is AX plus B, where A and B are those large vectors. So you can think of Vector OLE as many parallel executions of an OLE protocol where we constrain the receiver to always use the same X in all of the instances. So in some sense, in all sense, Vector OLE generalizes OLE the same way that string OT generalizes OT, and it still enjoys quite a number of very cool applications from MPC. I'll tell you more about that later. So first, our result. What we do is we build a way to compress, so what we call a Vector OLE generator. So we build a way to compress Vector OLE correlations, where you can start from small keys and locally generate long pseudorandom vectors A, B, and X, C, where C is AX plus B. And the security guarantee is that any of these players do not, from the view of any of these players, the value obtained by the other player looks random, constrained to satisfying this correlation that we want it to satisfy. We achieve this under the learning parity with noise assumption for any field. And it turns out that our result is actually quite efficient. So let me motivate that a bit more with a few applications of this. So if you have a possibility of generating with a very small communication random or pseudorandom Vector OLE, you can directly convert that to a standard Vector OLE, where you can pick A and B yourself and X yourself by standard cryptography, by standard techniques. And this directly gives a rate 1/2 Vector OLE protocol. Here, rate 1/2 means that the communication is essentially just the cost of sending A and B, plus something vanishing. And actually getting better than rate 1/2 under the assumption that we use LPN, that will lead to quite a breakthrough, because a better than rate 1/2 Vector OLE protocol that implies a form of commitment that we only know how to get under collision-resistant hash functions. And with the variant of LPN that we use, obtaining collision-resistant hash function will be a breakthrough. So in some sense, what we obtain is kind of optimal under these assumptions. Vector OLEs themselves, they have many applications in all kinds of secure computation protocol that involve multiplying one value by many other values. That makes sense, but I want to insist on the fact that this appears very often in real world applications of MPC. Think, for example, about matrix vector multiplication. You have a size n vector, you want to multiply it with a large matrix, then you just have to do n parallel calls to large Vector OLE to securely compute this matrix vector product. Or think of a nearest neighbor search, where you have a huge database of vectors. Each of them are quite short, and you want to compute the similarity. So you will want to do some inner product between like one candidate vector and all the vectors of this database. And if your small vector is of size n, that again can be reduced to just n parallel calls to a Vector OLE. And so if you can do secure Vector OLE with all this unique communication pattern that I've been telling about, like with tiny communication and computation and then only local work, then you get all these benefits for all this kind of real-world MPC application that use this Vector OLE. I think I won't have time to go into the details, but I'll be happy to discuss that afterward if people are interested. There are also more high-end applications of Vector OLE in related to arithmetic garbling or very cool types of non-interactive zero-knowledge proofs. If you want to know more about it, I'll be happy to answer questions about that. But let's go directly to how we did it. So the first observation is that if we want to have a pseudorandom Vector OLE, so pseudorandom A, B, X, and AX plus B, it suffices to have a sparse Vector OLE generator. So something, so what is a sparse Vector OLE generator? Well, first observation, you can easily think of B and AX plus B as being an additive share of A times X. So we'll think of it as being such. And what I called a sparse Vector OLE generator is just a Vector OLE generator where I restrict A to being very, very sparse. So A is zeros almost everywhere, except at a few locations where it can be anything else. And so a sparse Vector OLE generator generates an OLE correlation where A is sparse and B and AX plus B, they just are random additive shares of this sparse vector AX. So first, why would that suffice? If we can generate those, why does that suffice for pseudorandom Vector OLE generation? Well, the idea is just that under the LPN assumption, this gives us exactly what we need to expand a very small Vector OLE correlation into a large one. Why? Because the LPN assumption, so learning parity with noise, it states exactly this. You take a short secret, which is a vector over some field. You take a big matrix. And if you multiply the secret by this big matrix and hides and like kind of adds to the result a large random but very sparse vector, the outcome you get is indistinguishable from random. So now, what we can just do is give all those parties this very small Vector OLE correlation, and those keys that allow them to generate this sparse Vector OLE correlation, which is large. And then with direct calculation, they can use this matrix M, which is public, to expand this short Vector OLE correlation into a very long one, and make the output pseudo-random just by appending this sparse Vector OLE correlation as being the error vector. So that's exactly what we need to get pseudo-random Vector OLE in general. So now the question becomes, how do we generate a sparse Vector OLE? So here, the second idea is that a sparse Vector OLE generator, that's something we almost already know in some sense. So it's something that's directly applied from a tool known as multi-point function secret sharing. So function secret sharing, that's a way to secretly share a function between two parties, so that if I give, so that for any public input, x, the two parties can locally evaluate shares of f of x, given shares of f. For arbitrary functions, that's super hard to do. We know how to do that, but we need high-end cryptographic primitives. But it turns out that for very restricted type of function, such as point function and multi-point function, which output 0 almost everywhere and non-zero at a few points, then a sequence of work by my co-author, Niv Gilboa, Yuval Ishai, and Elliot Boyle, have shown that this can be done actually extremely efficiently, starting from any pseudorandom generator. And that's really very efficient. And that's exactly what we need, because if you have a function secret sharing for k-point function, well, these sparse vectors that you want to share between the parties, this is essentially just the truth table of your k-point function. So you just have to share this point function and let the parties evaluate it on all points of the domain, and they will locally obtain shares of a very sparse vector, which is exactly what we need. So once you combine both, you end up with a quite efficient way from any pseudorandom generator together with the LPN assumption of generating pseudorandom Vector OLE correlation. We can improve that further. If we use a dual variant of LPN, we can go from what I said previously, only allow for a quadratic expansion. We can actually even go to near arbitrary expansions. We can improve the evaluation time to linear time using batch codes. I won't go into the details. It's just skimming through some things we've done. You have a number of heuristic optimizations that you can apply to make that more efficient. You can use more LPN-friendly linear codes to improve further the efficiency. And all of that gives you a very strong efficiency. Like if you want to generate, say, a Vector OLE, pseudorandom Vector OLE, of size 1 million over a 120-bit field, and 28-bit field, then this can be done. It's an estimation. We've not implemented it in, say, 26 milliseconds on one core of a standard laptops, a few dozen milliseconds. Even if you only wanted to generate Vector OLE, even if you don't care about this unique communication pattern that you can have with like tiny computation communication, local work and everything, what we get is extremely competitive with previous approaches. There was a work at Crypto 17 last year that shows how to achieve Vector OLE from similar looking LPN style assumptions with an asymptotic rate of 1/3. So you to have n-bit n elements OLE, you need 3n elements of communication. But if we apply our work with our new method, we get a better asymptotic rate that also translates in practice to better concrete communication. And more importantly, the estimated computation cost can be up to 2 orders of magnitude smaller, the computation cost per OLE that you obtain there. And conceptually, most of the improvement here comes from the fact that in this previous work from Crypto 17, some more involved erasure decoding techniques needed to be applied to compute the output, while here we avoid all of them. We never need any complex erasure decoding of our noisy linear samples. We only need encoding. So everything is just plain, simple field operation, addition and multiplications. With a result of Donner and Shelat from CCS last year, we can make the distributed setup for our protocol actually quite efficient by making a black box use of the PRG. So the number here are quite good. If you want, again, 1 million entries in your Vector OLE, you just need 34 milliseconds of computation in total. Again, it's an estimation. And on top of all of that, we have this unique communication pattern where you can enable this Vector OLE generation with almost nothing in terms of computation, communication, and only when you need it, you can locally generate it. And that's really an advantage that no concurrent work offers until now. So I think it can be useful in quite a wide variety of applications, and I'm sure you can find some use to it. That's the end of my talk. Thank you for your attention. Do you have any questions?
Hi, maybe I have a question that I didn't understand something, but you said you used batch codes. What instantiation of batch codes did you use?
So yeah, we need a combinatorial batch code. So so the question is, why do we use them for, or which type of batch code?
Which type of batch code?
Combinatorial batch codes. So that's those from the initial paper where you will essentially randomly
and you
create a bipartite graph.
You implemented it with this batch code?
We didn't implement it.
Oh, okay.
And the batch, actually, when I mentioned heuristic optimization, if you want to implement it and use it in practice, there are heuristic optimization that will give you more efficiency than batch codes. But with batch codes, we can get the same asymptotic result of linear time evaluation, still under the standard LPN assumption. But you can have way better constants using more heuristics, which in practice will be the way to go.
You mean cuckoo hashing? What do you mean by heuristics?
Essentially, what you need to do is to generate an error vector, to generate this vector in linear time. And yeah, the reason why we needed the cost by default is not linear is because with function secret sharing, we essentially need to make a pass over the entire data for each of the sparse points that we want to add in our sparse vector. And you can either make this like linear time with batch codes, or use another error distribution, say like a regular LPN, where you will just break your vector into small portions and add one noisy coordinate in each portion. And if there's this variant of LPN, then you directly have a linear time cost for generating this error vector, but you do not rely directly on the standard LPN anymore. That's kind of what I mean.
Okay, thanks.
So I have a question. Yeah. You said you didn't implement it.
Yes.
But you have these very precise running times. So how do I reconcile those things?
Yeah, so we plug, essentially because the computation we do are very simple. It's a very precise number of field multiplication and nothing else. Like field multiplication and black box code to, say, a PRG. So we just plug in the number for what it costs for like a hardware AES in there, and of some implementation of some field multiplication. Of course, an actual implementation will give different running times. It's just that numbers are more visual than rough estimation. But yeah, I insist, if you actually implement it, you'll likely not get exactly the same numbers.
There are these things called caches, which fill up very quickly, and then
Yes.
you have much slower I/O time for
Yeah.
et cetera, et cetera, et cetera. So I encourage you to implement the.
Anybody who ever reproduced the numbers in any science paper?
I think maybe we should take this one offline, but I feel if you have numbers, then they should really be based on something solid. So any more questions?
Implementation of that point function.
Yes?
Okay.
Can you?
Yeah, it's just for a different paper. We implemented it.
Ah, okay.
Okay, so one more question for me. So you're using LWE, but you're using sparse secret LWE.
LPM.
Oh, you don't use LWE.
No. So LWE, it's you add Gaussian noise everywhere. Here we add complete flooding noise, uniformly random noise, but only at a few locations. That's exactly LPM. And this is considered to be, even though we don't have any direct relations between the two, this is usually considered to be a more conservative assumption than LWE, essentially because we know far less attacks on that. The attacks we know, it seems even harder to find non-trivial attacks on this. And we also know far less important cryptographic primitives from LPN, so it's also usually considered a harder assumption to work with, but it's a quite good one.
Okay, I think it's coffee time, so let's thank the speaker.